Okay, in this one I wanted to discuss three very important derivative rules. So there's one, the power rule. Um, the second one is called, well, it's just the derivative of a constant. So I'm going to say derivative of a constant. I'm just going to call that C. And then the third one, it's pretty much just an application of the power rule, which is just the sum or difference rule, plus or minus rule, right? So let's start with the derivative of constant rule because it's, with the most basic. So, well, the derivative of constant. I'm just going to use this notation. It's called, well, it's a derivative operator, right? So it's like you take the derivative in respect to x. So it's an operator that's applied to a function. So in this case, it would be c, like I said. And that, well, that's just equivalent to 0, right? Because, well, a constant is not changing with respect to x, right? If you have a linear function y equals 3x plus 5, this 5 is not going to change if you change the x value, right? Or if the slope changes. So it isn't the slope. And so yeah, it's equivalent to 0, and that's quite basic. So the second rule, the power rule, says that if you take the derivative with respect to x of a function x to the n, so it's some polynomial. So you cannot, so this n value right here has to be constant. So x cubed works, x to the 1/2 works, anything where the exponent stays constant, but 2 to the x where the exponent is changing in an exponential, that doesn't work. So with that being said, essentially what you do is you take this nth power, you bring it in front of the x as a coefficient, and if there's already a coefficient in front of it, you just multiply the n by that coefficient. But in this case, there's no coefficient. So you just bring it down so it becomes nx, and then take this nth power and you decrease it by 1. So you just add and subtract 1. Okay? And then plus or minus rule, like I said earlier, was, it's just taking the power rule. Well, for a polynomial at least, because you could have sum or differences of other functions, but for sum or difference of a polynomial, you're just using the power rule essentially. So if you have two functions, f of x, just two arbitrary functions, f of x plus g of x, is equivalent to the sum or difference, so plus or minus, of their derivatives. So essentially, you take the derivative of this first term, and then you either plus or minus, depending on the question, the derivative of the second term. So it's just f prime of x plus g prime of x, right? So yeah, those are the three basic derivative rules. They're quite useful because you don't have to keep on using the limit definition. So yeah, like we said that the drawing a tangent line is quite annoying, but we're getting lazier and lazier, so now we're just going to say that the first principles limit definition is also tedious, and it is, right? I mean, these are some basic functions that you have to, plug in and like get rid of the denominator. So yeah, these are some good rules. So I'm just gonna do a couple examples. So the first one I'm gonna do is f of x is equivalent to x squared. So this was the curve that we were looking at the last lesson. So we want to find f prime of x, the derivative of x squared. And using the same rule, we bring this exponent down, so it becomes 2x, and we decrease this exponent by 1, so it just becomes 2x, because x to the 1 is just x. So 2x is your answer, and that was found quite considerably quicker than using the limit definition. And it gets even more and more useful as you look at more composite functions, like I said, with the, sum and difference. So if you consider this, f of x is equivalent to x cubed plus x squared plus, 6x minus 5. So f prime of x is equivalent to, well, let's first find the derivative of x cubed, the d dx of x cubed x cubed is equivalent to 3x squared, right? Take this exponent, bring it down in front of it. So you take the 3, you bring it down, and it becomes 3x squared, and then you decrease the exponent by 1, so it becomes 2. So that's our first thing. And like we just said, for the x squared, you just take the 2 down, and then you decrease by 1, like we said here. So it just plus 2x. Now, whenever you're looking at a linear function, you could either just, take it with the derivative rule. So derivative with respect to x of 6x is equivalent to, well, you can imagine a power 1. So if you bring down the power 1, well, it doesn't change anything. So it becomes 6 and then x to the 0 power, right? Because you're decreasing by 1. And anything to the 0th power is just 1. So it just becomes 6. And another way you could just think about this, which is much quicker, is that it's a linear function. The slope of a linear function is the coefficient in front of the x. And that's pretty much it. So plus 6. And now we said that the derivative of a constant is 0 because it doesn't change with respect to x. So negative 5 is just 0. And I don't need to write it out because, no point. So that's the derivative of that one. Now I want to look at a little bit more complex. Not much more difficult though. So f of x is equivalent to, let's see, the cube root of x plus 5x squared plus pi to the 4th power. So first things first, so f prime of x. So we're going to take care of this first term. So the problem with this one is you'll say, well, the power rule only applies when you have a power. I mean, this is a radical, this is not a power. But if you remember that, you can convert radicals into exponents. So, it's just a fractional power. So if you have the cube root of x from, algebra 2, I think it is, it would have just been x to the 1/3, right? Because this is a power 1, you make the root the denominator, and yeah, that's what you get. So now we could say, well, what's the derivative with respect to x of x 1/3? So recall that we bring the exponent down, so it becomes 1/3 x, and then we take that 1/3 and we minus it by 1, so minus 1. But in this case, just because we're subtracting fractions, we can just write it as 3/3. So we can simplify the exponents down, and it becomes 1/3 x to the negative 2/3, right? Because 1 minus 3 is just 2, and then you keep the denominator same. So yeah, you get 1/3 x to the negative 2/3. Next term, 5x squared. Now remember, I'm not sure if I said this or not, but if you have an exponent and you need to bring it down, so 5x squared, let's find the derivative with respect to x of that. So derivative with respect to x of that. So we just said that if there's already a term there, you just take this exponent and multiply it by the coefficient in front. So it would be 5 times 2, and then x, well, 2 minus 1, right? So simplifying this down, you get 10, because 5 times 2 is 10, and then x to the 1, right? Which is just 10x. So now we can add that on, so plus 10x, and then I'll just, kind of clean this up a little bit. So now we just have the final term. Well, this is 0, right? Because obviously, it isn't 4 pi, because this is just a constant. Pi is a constant. So yeah, this is just 0. I don't need to write that because, it doesn't make a difference. And yeah, that's a basic idea. Well, yeah, one more thing. You can leave this by yourself, like by itself, but you can also simplify this, and it would just be 1/3 x, or sorry, cube root of x, cube root of 1/x squared, right? So yeah, you take this denominator, you put it back, and it becomes a radical, and then x to the negative 2 is equivalent to the reciprocal of the positive x squared. So yeah, 1/3 cube root of 1 over x squared. So yeah, those are the three, well, important derivative rules, and they save a lot of time when dealing with more complex functions, so you don't have to keep on plugging them in. So yeah, hope that helps, and yeah, bye.